Welcome to the introduction to the field of chemical kinetics. At the beginning of this introduction, we will bridge the concepts of thermodynamics and the dynamic behavior of chemical systems. Thermodynamics allows us to understand the driving forces of chemical reactions. It primarily focuses on the equilibrium state where the change in Gibbs energy, delta G, is zero. It tells us if a reaction occurs spontaneously and what should be the final state of the chemical system, but not when or at what rate it will reach equilibrium. This is where chemical kinetics comes into play. Chemical kinetics measures and describes the progress of a chemical reaction towards equilibrium. It provides the temporal dimension that thermodynamics lacks. By studying the temporal evolution of the system toward equilibrium, we obtain insight into the details of the reaction dynamics and mechanisms responsible for this evolution. These details are beyond the scope of thermodynamics alone. Broadly speaking, chemical kinetics is a branch of physical chemistry that studies the rates of chemical reactions. In this course, we will explore several key questions. The first question is what precisely is the reaction rate? Through which methods can we measure and quantify this rate? What parameters affect reaction rates and how do factors like reactant concentrations and temperature influence it? According to which mechanism does the transition from reactants to products proceed? And finally, how do catalysts function and in what ways can they modify reaction rates? The central concept of chemical kinetics is that by monitoring the rate of a chemical reaction and determining the dependence of this rate on system parameters such as temperature, concentration, and pressure, we can gain insight into the mechanism of the reaction. Experimental chemical kinetics includes the development of techniques that allow for the measurement and analysis of chemical reaction dynamics. In addition to experiments, theoretical work has been performed to understand reaction mechanisms and the underlying physics that govern the rates of chemical reactions. The subject of chemical kinetics is not just an academic curiosity, but a crucial part of both basic and applied sciences. It also has practical implications that touch upon various aspects of everyday life. Generally, it allows us to understand and predict the speed at which reactions occur. This understanding is crucial across multiple domains. In the realm of the chemical industry, the role of kinetics is foundational, particularly in the field of catalysis. Chemical kinetics helps us understand reaction mechanisms. By studying the steps of a reaction, chemists can design catalysts that speed up reactions, leading to more efficient processes. Catalysis in the chemical industry is centered on accelerating chemical reaction to synthesize materials both efficiently and on a large scale. This acceleration is crucial for the production of a wide array of materials, ranging from everyday plastics to complex pharmaceuticals. Chemical kinetics is particularly important in the development of sustainable chemical processes that minimize energy consumption and waste production, aligning with the global shift towards environmentally conscious manufacturing practices. In pharmacokinetics, kinetics helps us describe how drugs are absorbed, distributed, and exerted by the body. It informs us about the frequency and dosage of medication intake, its potency, and the rate at which it is metabolized. This is essential for patient safety and the efficacy of treatment. Enzyme kinetics is another important area focusing on enzyme-catalyzed reactions. This branch is fundamental to biochemistry and drug design, with implications for understanding metabolic pathways and designing drugs that can modulate these pathways. In archaeology, kinetics provides tools such as C14 dating method, allowing us to determine the age of ancient organic materials, from mummies like Ramses and Ötzi to historical artifacts, giving us a window into the past. Moreover, chemical kinetics is fundamental in environmental chemistry. It allows us to predict how pollutants will behave in the environment, how fast they will degrade, and what products they will form. This knowledge is crucial for environmental protection and remediation efforts. Lastly, chemical kinetics plays a decisive role in the field of renewable energy. Our research group, for instance, investigates how we can optimize energy consumption using renewable sources. Kinetics is key to understanding and improving processes like wind and solar energy conversion, as well as energy storage solutions such as batteries, fuel cells, and electrocatalysis.